Justin, this is Shalwin, and this is Ashwin, and we are from Taylor's University. And
so we were given a task. We were actually given a cylinder with a certain radius and a certain height. Okay, so we were tasked to change this radius and the height, but using values that would actually save cost. Yeah. But then we actually could not change the volume of the cylinder. So we had to use calculus and differentiation and stuff to help find the two values.
So, as Ashwin explained earlier, we had to make a cylinder that would hold up the same amount of things in terms of volume, but at the same time, we had to be more economical in the way we made the cylinder. So, in doing so, by using calculus, we managed to find the proper radius and the proper height where we could make a cylinder with the same volume, but still, for the price, we made it cheaper. And so I'll show you how it's done. So first, the radius that was given was 3.25 centimeters and the height was 16 centimeters. And so what we did was, we could, since V equals to pi r squared h, this is the volume of the cylinder, we can derive that h equals to V over pi r squared. And once we know that the surface area of the cylinder, once you open it up, you know that it's 2 pi r squared plus 2 pi r h. And so if you substitute the h into this part, you would get something like this: 2 pi r squared plus 2b over r. And so once you have this, now what I'm going to do is I'm going to differentiate a in terms of r, and you'll have something that says 4 pi r minus 2b over r. And since you have this now, this will now be equivalent to 0, and you'll get something. If you let r stay here and you let the rest go over, you'll get something that looks like this: r equals to cube root of b over 2 pi. And so if you substitute the v from the v is actually, once you calculate the v, it's actually 530.9 cm squared. We are leaving it in cm because it was given to us in cm, but you can change it if you want to. And if you calculate this, your r, you'll get a value of 4.39 cm. And once you get that, you can find your h using equation number 1, which you will find out to get 8.77 cm. And so now to prove in terms of economic, financial wise, which one is more economical, the initial cost, which is basically you have to calculate the surface area of the side of the cylinder and also the top and the bottom of the cylinder. The initial cost, which is 2 pi r squared times 32, because the top and bottom is 32 ringgit, plus with 2 pi r h, which you have to times with 25, because the sides is 25 ringgit per meter squared, and you will get something like RM 1.04, so 1 ringgit and 4 cents. The final cost, however, using the same equation, but only the r we are taking as the r that we found and the h that we found, our final cost would be RM 0.99. So 99 cents and 1 ringgit and 4 cents. We have created the same sort of cylinder in terms of how much it can contain, the same volume. Only thing this time we created a better one because we are providing it for a cheaper cost So economically, I think we have managed to overcome the scenario that has been given. You can see that earlier we have proven that we've chosen actually the cylinder to show you how the price, we have decreased it by 5 cents and we managed to save up 5 cents. And using this, we also tried with Prism and we also tried with cuboid, and we think that the cylinder is the best in terms of the structure of it, the products it can hold, and also secondly, it saves the most amount of money. So that's why we have gone with the structure and of using cylinder.
So what we actually learned through this entire project is how do we actually use calculus to save money. Okay. In this case, we actually saved only a very small amount, which was about 5 cents. But when we go into real life situations, we can see other major companies ordering larger amounts of materials. They can actually benefit a lot by using methods such as this. Okay. So in the end, in short, we actually managed to take a cylinder which had two totally different, not optimum values, but we actually used calculus to find the optimum values, but then at the same time maintain the maximum volume it could take. Yeah. So thank you.